We are in a collaboration, which is the so-called CROW collaboration. CROW is a satellite, and it observes fields, and we are looking for planets which are transiting the star. That is, we are looking at stars and the planet is crossing in front of the star. And because the satellite is in space, it can measure the dimming of the star, because a black object is crossing the stellar disk to a very high precision, better than 1 in 10,000. And that's not really possible from the ground. And in this way we can detect the transits of very small planets. Now, of course, the satellite is nice to detect these transits, but when we just measure the transit, we only get the ratio of the radius of the star to the ratio of the radius of the planet. So what we need is the true radius of the star. We need the stellar mass, and we have to measure the mass of the planet by using, yes, exactly, radial velocity measurements. And so when we get a good candidate, we are first observing it with, say, medium-sized or small telescopes. And the first thing is to take a spectrum of the star to see if it's solar-like or if it's a giant. If it's a giant star, of course, then the object which is transiting is big and not very interesting for us. So what we do here is we take a spectrum with a low-resolution spectrograph of all the candidates first, in order to know if it's an interesting object or an object which is no longer interesting. If we did this, the next step is actually taking images. The satellite is very good, but the imaging quality is limited because the image is slightly defocused to get a high photometric accuracy. And for that reason we are taking an image to be sure that the transit is really on the bright star, but not on a faint star within the photometric mask of the satellite. So imaging is then the next step, and the third step is radial velocity measurements, for which we are also using our telescope, but also when it's really a very low mass object, then we actually need a bigger telescope. So we are then using also the VLT, and we are also using the very large telescope in Chile for doing imaging. Now, the interesting thing which you might ask is, here we are in the northern hemispheres and the telescope on the southern hemisphere, and the fields which CROW is observing are on the equator. So we can actually use telescopes on the northern and the southern hemisphere to observe these fields, and that's very typical for our work. We are always networks of little telescopes, medium-sized telescopes, big telescopes, and each is taking a bit of the work, and all the telescopes combined are really doing the science. And so this is a combination of space telescopes and various types of telescopes to do these different kinds of work, and this is all defined in this way. And to some extent we are not making discoveries just with these telescopes, but with all telescopes combined. But surely the most important discovery which we have made is the first planet actually where we know that it's a rocky planet outside the solar planets, solar system. We know in our solar system Mercury, Venus, Earth and Mars. These are the rocky ones. They have high density. In principle, you can walk on all of them. And so far, outside of our solar system, all we knew were the gas giants like Jupiter. In order to be sure that there's a rocky planet, one has to measure the mass and the diameter to get the density. And we found one planet which has a mass which is higher than the Earth. It also has a little bit larger radius. It's 1.6 times the radius of the Earth, but we measured a density which is of the order of 9 grams per cubic centimeter. And because it's a little bit larger, the density is higher than the Earth, but for sure we know that it has such a high density that it must be a rocky object. And this was the first time that a planet which is known to be rocky was found outside the solar system. So from this planet we know that there are, to some extent the Earth is not unique, but there are other planets like this in the sense that they are rocks and not only gaseous giants like Jupiter. And we had taken a low resolution spectrum of this star, of this candidate, and we recognized that it's a solar-like star, and so the object which is transiting had to be extremely small. And from then on we did actually a lot of observations with all kinds of telescopes which we had, and at the end we draw a conclusion that this is really the object, the first rocky one. And actually we were so interested that a year later we repeated the whole observations and went back and observed it a second time with a satellite and a second time with ground-based telescopes to confirm the results and to learn more about this object. And even up to now there are only 2 planets. We know in total about 800 planets, but only for 2 of them we are sure that they are rocky because we have the mass and the density. And so it's still a very rare species of planets, and that's why it's so interesting to study these objects.
Can you remember what's the period of this planet?
Yes, this is very funny because it's less than, the orbital period is less than 1 day. It's orbiting in 20 hours. So it's a very close planet, and that makes it also so interesting. How did it form and why is it still there? It must be very hot, and people calculated what could be the surface temperature, and basically if it's a rock it would be heated so much by the star that the rock should melt and should be basically lava. One side, which is
we say this is a rocky planet, but in fact this is a melting rocky planet.
It's at least one side should be melted. It should be covered with lava. So we thought, okay, we even made the next step, and we said, if it's melted, then in principle there are certain elements which evaporate also in volcanoes. So we could also search for, say, this volcanic plume or this volcanic eruption, which we tried. And unfortunately we didn't detect it, but maybe this was only the sensitivity. But we followed this object and we think it should be a molten rock, and maybe it is possible to detect the kind of atmosphere of this planet in the form that it would be more lava-like, or like Io in our solar system, which also has volcanic plumes and so on. Maybe such events could be discovered in this planet. Up to now we haven't done it, but maybe this is just a matter of sensitivity. If we continue, or if we use in future even larger telescope, maybe there's a possibility to yes, to discover also the volcanic activity on a planet outside the solar system. Other discoveries which we made was a planet of a relatively young star. And this is interesting because we want to study also the evolution of planets. And up to now the planets that had been found were all orbiting relatively old stars, and we found also a planet which is orbiting a young star, a transiting planet. So we can also test the theories of planet formation with this object. And the other thing is, because it's a young star, the star itself is quite active, and we can study the effects of stellar activity on the properties of planets. Yes, and one of our planet has been also detected directly, so that the temperature of this planet could be measured. And because most of the planets we discover now are close-in planets, the temperatures are very high and can be very often several thousand degrees. And in the case of some of these close planets, we also know, because one side is heated, we know that there are strong winds in the atmosphere. So for most of the planets it's very funny, we just discover them indirectly, but we already know some details. We know their mass, their size, the density, and for a few of them we already know the temperature, and we also know that some of them have winds in the atmosphere.
So you say we still coming closer and closer
yes.
to the rocky planets and the like super Earths, maybe
yes.
Earths.
Yes.
And coming to this region which is called habitable zone.
Yes, habitable zone. But there, I would be a little bit more open-minded, because we fix the habitable zone from the conditions of the Earth. The habitable zone is the zone where liquid water is possible. But on the other hand, when we look around in our solar system, the Earth is not necessarily the only place where there could be life. I mean, for many years people are studying Mars, and of course there is not life like on the Earth. There are certainly no trees and no animals running around, but of course there could be primitive life below the surface of Mars. And the other say ecosystem in our solar system is perhaps the icy moons of Jupiter, particularly Europa is very interesting. There is a ice crust, but underneath there could be an ocean, and there is good evidence for the ocean. And people are speculating that life could exist in this ocean. And of course, such object could also be, in a sense, be habitable and forming different kinds of ecosystems. And so that the so-called habitable zone could not be the only region where there could be life. And one can imagine that these icy objects are not that rare, and there could be many objects which harbor life but are not in the habitable zone or not in the classical habitable zone. The same with Mars. Mars is, say, at the outer edge of the habitable zone. If there is life, then certainly this life could be different from Earth, but still such an ecosystem could exist. So we should not be so narrow-minded and just think of life on Earth. There could be many different ecosystems in the universe. But one story which we should always remember is the story of the, say, life on Mars. If you think back there 100 years ago, people really believed that there is even intelligent life on Mars, and that there are forests and everything, the channels and so on. And 100 years ago, actually, in France, there was a prize of the person that first makes communication with intelligent life with another planet. But the woman that offered this prize said, except for Mars, because for Mars it's so easy that this is not worth the prize. You have to make the communication with another civilization, but not the one on Mars, because this is too easy. So people were very convinced that there's life. And then the more research was done, then they said, okay, it's not intelligent life, it's mostly a desert. But still in the 1950s, when the people had the first infrared spectra, they believed that at least that there are plants on Mars. Mm-hmm. And actually the spectra were not that bad. They were done with, from modern standards, not so great detectors, and something else went wrong. But at that time, there was still the hope that there's at least primitive life form on Mars. Yeah,
I remember I read some astronomical book, a quite serious one.
Very serious.
And it told with such kind of, it is quite probable that there are some plants on Mars. Because there are some season changes of colors there.
Exactly.
They're watching that, and they deduce that it might be vegetation there.
And even I think the first landers on Mars, they said the cameras should be made such that possible animals which are walking by can be found. And this was very serious. So,
you mean the first probes, something
yes,
like the 70s?
The first probes, the Viking probe, they actually thought, always keep in mind that maybe on the images that there are some animals walking by. And so at that time the people were thinking of this, and today we know that there are no plants and certainly no animals walking around, and we are looking now below the surface. But so to some extent we have this evolution of the Mars exploration. We first started with intelligent life and really forests and lakes and so on. Then we thought, oh, maybe some little plants, and then we said, oh, maybe it's single cell things on the surface. Now we are saying single cells below the surface. And with extrasolar planets it could be the same. We first think now that we will find very easily planets with life like in the tropical rainforests. That would be much easier to detect than if the life is, or typical life is more like Antarctica. That would be, there's still life in Antarctica and also in the Arctic Circle there's life, but this would be far more difficult to detect. And at the moment we are very optimistic and said maybe the planets look like the tropical rainforest. And we are thinking of these kinds of things, but if most of the life is more in the life form of the Arctic, then it will take much longer to detect it. And if it's like an ecosystem like Europa, where you have ice and an ocean below the ice, then it will be super difficult to detect.
Anyway, they are designing some probe even to penetrate into that ocean.
Yes,
and
yes.
This expedition is scheduled, if I'm not mistaken, to the 2022, something like this.
Yes, yes. And what is very positive is that in the case of Enceladus, the moon of Saturn, there seems to be a similar situation, ice and maybe water underneath, but Enceladus has the great advantage that there are some cracks in the ice and some of these water is in plumes coming out. Yeah. And it's already known that there are complicated hydrocarbons in these plumes, which is of course an interesting step in terms of life if there are these complicated hydrocarbon molecules. And amino acids are also in these plumes, which is of course a very interesting discovery. It's not life, but it's at least chemically the steps towards life. So I think we can be mildly optimistic that in such an environment, at least the chemical reactions are ongoing which are in the direction of life, so we can be mildly optimistic that there is something.
At least these satellites, they have their internal source of warmth.
Yes, yes,
and
yes.
Like Enceladus, like Europa,
yes,
like
yes.
EU, by the way, and they can just warm up their interior in order to do these chemical reactions. I was very impressed getting to know that there's simple salt out of Enceladus. This is really great.
This is fantastic.
Yeah.
And as far as I know, there are a few lakes underneath the ice in Antarctica, and people are interested in finding out if there's any life forms in there. And recently they made a drilling in one of these lakes, but one lake which has a little connection still with the ocean, and they were thinking of maybe finding single cellular life or something in, but what they discovered is a shrimp. So already a very advanced animal, but of course this lake had a connection with the outside ocean. But it means that in such an ecosystem, maybe that there could be something also on other bodies in our solar system. And so we should also, in terms of exoplanets, be prepared to think about such ecosystem also outside of our solar system. And learning more about these distant worlds and so on could be very interesting.
Looks very exciting. Looks very promising.
Yes.
You're working in real interesting and exciting field. You're
Thank
very
you.
lucky.
Thank you.